Ever wondered how EVs get from A to B? Is it essentially the same as an internal combustion car, but wired up to a giant battery? Or is there some altogether more subtle trickery afoot? Join us today as we pop the frunk and ask, how exactly do electric engines work? Surprisingly, the operating principle behind most modern electric vehicles predates the internal combustion engine by a number of decades. In 1834, a Dutch professor named Sibrandus Strating of Groningen, Netherlands, built his own small electric vehicle. The catch being, its battery was non-rechargeable. Internal combustion engines work on the principle that fuel and air, when compressed and ignited, cause a tiny explosion. That's the combustion part. This explosive force pushes a piston. That piston's linear motion, in concert with a team of fellow pistons, transforms into rotary motion via a mechanical crankshaft. This in turn spins your wheels along the highway. Conversely, the fundamental principle that drives electric cars is magnetism. Everybody knows how opposing poles on a magnet attract and how alike poles repel each other. So let's imagine an experiment using two magnets, one fixed, the other mounted on a nearby rotating shaft. If the two poles nearest to each other on both magnets share the same polarity, say north to north, the magnet on the shaft will be repelled. Because it's attached to a shaft, the shaft will turn. That is until the south pole on the shaft magnet is aligned with the north pole on the fixed magnet, whereupon the shaft will again be still. In our imaginary experiment, we've made the shaft turn a half rotation. All very well, but that won't get us very far on the morning commute. Here's where electromagnetism enters the chat. In a fixed or permanent magnet, like the kind you have on your fridge at home, those magnetic poles are rigid and never change. North is always north, south is always south. On an electromagnet, however, which is essentially a core of metal coiled in electrical wires, this magnetic polarity can be reversed. Imagine one of our experimental magnets is now an electromagnet. If the south pole quickly flips over to north, the fixed magnet will yet again repel the moving magnet, rotating our shaft another half spin. That's a whole spin now. We're slowly getting there. For a basic illustration of how this polarity reversal works, imagine a very simple circuit involving a battery and a light bulb. Electrons flow in one direction from the battery, through the wires, to the light bulb, and back again to the battery. If we remove our battery from the circuit, flip it 180 degrees, then replace it in the circuit, those electrons will still flow around the circuit, just in the opposite direction. Either way, the bulb lights up. Electromagnets, like light bulbs, work whichever direction the electrons are flowing. But rather brilliantly, the polarity of the magnet gets reversed with the flow of electrons. So to keep our magnets in permanent repel mode, we just need to keep reversing the polarity of the magnet. How do we do that? One way would be to keep popping out the battery and flipping it around. But that's a lot of trips to the mechanics with your EV for the sake of a few feet of ground covered. So the real trick to making our magnet spin, which is essentially how electric motors work, is through the so-called inverter. The inverter module on the EV draws direct current from the car battery and, through a clever combination of quick switches, slick circuitry, and capacitors, flips the flow of electrons back and forth nearly 60 times a second. Domestic electric motors, like the one you have in your hairdryer, don't require an inverter. Why? Because the current that comes from your wall outlet already flips back and forth. That's why it's named alternating current, or AC. Batteries of any type can only ever produce DC, or direct current. So, spinning magnets, driven by alternating current passing through coils of wire, is essentially what drives electric cars. Electric powertrains have a number of advantages over the internal combustion engine. For starters, the motion produced by the motor is already rotary in nature. Dirty pistons on an ICE require a complicated breakable crankshaft just in order to turn their linear motion into rotary movement. So EVs are less likely to fail or require expensive, time-consuming maintenance. Here's another clever thing about that inverter. By adjusting the frequency and amplitude of its newly created AC current, the vehicle's speed and torque can be finely calibrated by its driver. There's no such fine control built into an explosively hot internal combustion engine, which is why expensive and accident-prone additions like gearboxes are a tiresome necessity. Another nifty detail about any EV's powertrain is when the shaft-mounted magnet, or rotor in engineering parlance, is itself spun, it generates electricity. This reversal very handily recharges the car battery. How can the rotor be turned, you ask? With any hefty source of kinetic energy, like say a braking automobile, which is handy. This is, to be clear, a very simple overview. There's different types of electric motor, and refinements to the design are happening all the time. Not least at one particular Californian car company named for the 19th century